Thank you for listening to my first talk on JavaScript. This is about Postgres. We're doing almost the same thing, but to Postgres database to SQL. SQL ain't JavaScript, so there is the same thing, but the language is much better. Not only it isn't dynamic, but X and Y and SQL, we know exactly offsets into tuple. So we have tuples in memory, and X and Y are offsets. So we are not only winning on getting rid of interpreter and doing JIT, but also with those offsets, this way it takes 56% in profile, this way only 6%. But this is really boring because it's straightforward. The interesting part is how to optimize all other stuff. This is a typical query from TPCH. TPCH is a benchmark suite mostly like Spec 2000 for compilers, but for database, for analytical processing. So they all have hot places in different parts. And SQL part, where part of the query is exec_qual. And only few tests have hot parts in exec_qual. So we need to optimize other parts like this one. Excuse me. This is aggregation. So we basically want to move from this model. We have interpreter, which have a query plan of nodes, and it goes node by node and interprets it. We go to this model. We have a plan, we compile it, and the code interacts with the database. We can do it two ways. First is semi-automatic. Of course, we can rewrite everything manually, but Postgres is a product with a long history, and it gets new features every week. So if we rewrite it manually to LLVM, the code, it will be maintenance hell. So we need some automation for JIT compilation. First of all, we want to rewrite this one. In Postgres, there is a workflow with virtual functions. So we start with aggregation part, and this count asks this model, and it can be different methods for scan. That's why virtual call. Virtual calls are not very good optimized. So we have this model that top level part of the query asks the underlying parts. This is slow. We want to make it more natural way, so we traverse database and filter it and then do aggregation. Then LLVM can inline one into each other and make it faster. Then there is a backend, functions like adding two integers. This is Postgres code. We can compile it with clang. Then we can compile it back into the LLVM API with CPP backend. So we can generate LLVM code for these functions automatically. And that's what we do. Then not only we can inline these passes, but also in filter we inline calls to backend functions and optimize them and specialize them. This is our model for semi-automatic conversion. C to bitcode to big backend BC, then optimize it, then back to backend CPP that can generate all the backend with LLVM API. So semi-automatic method switches from Volcano style model to natural, make use of LLVM inlining, and automatically backend. Okay, and we want something more automatic. We want to specialize Postgres code with a pointer with a plan.